Here is something that I find genuinely fascinating. When you train an AI model, every update you make leaves a mark inside the weight matrices of that model. And it turns out that different training methods leave completely different kinds of marks. Not just different in magnitude, but different in their geometric shape, their location, their structure. And a new piece of research has done something that nobody had quite done before. It mapped out the geometry of three major AI training approaches and discovered that one of them, a method called on-policy distillation that is rapidly gaining popularity, does something completely unexpected and unique.
Okay, so you're talking about training large language models. Most people know there are different ways to train AI, but why does it matter how the weight updates are shaped geometrically? At the end of the day, does the model get smarter or does it not?
That is the natural question, and it is a fair one. But here is the thing. If you only measure whether the model gets smarter, you miss a huge amount of information about why it works and when it might fail. Imagine you had three different athletes who all ran a marathon in the same time, but one of them burned through all their energy in the first half. Another one paced themselves evenly, and the third one somehow found a highly efficient groove they could hold indefinitely. The final time looks the same on the scoreboard, but the underlying mechanics are completely different. And understanding those mechanics is exactly what tells you how to make the next generation faster.
So walk me through what these three training methods actually are, because people hearing this might not be familiar with all of them.
Sure, the first is supervised fine-tuning, or SFT. This is the most straightforward approach. You take a large language model and you train it on examples of correct answers, essentially saying here is a question, here is how a smart person answered it. Learn to produce outputs like this. The second is reinforcement learning with verifiable rewards, which you can think of as teaching the model by giving it a grade at the end. The model produces a full answer to a math problem. You check whether the answer is right, and you reward or penalize the model based on the outcome. The third is on-policy distillation, which is the newest and most interesting one in this research. Here you have a weaker student model and a stronger teacher model. The student generates its own answers, and while it is doing so, the teacher is looking over its shoulder at every single word and providing dense, step-by-step guidance on where the student went wrong.
That third one sounds like it has elements of both the others. The student is generating its own outputs like in reinforcement learning, but it is getting dense token-level feedback like in supervised fine-tuning. So why would it not just behave like a combination of the two?
That is exactly the assumption the researchers were testing, and the answer is, it does not. This is the surprising finding. Everyone assumed on-policy distillation would sit cleanly between supervised fine-tuning and reinforcement learning in terms of how it modifies the model. And in some static measurements, it does sit between them. But when you look at how those updates evolve over the course of training, the trajectory is completely its own thing. It is not a temporal blend of the other two. It follows a path that neither of them takes.
Before you get into what that path looks like, you need to explain what you mean by the geometry of weight updates. What does it mean for an update to be geometric in a specific way? I think this is where people might get lost.
Great point. Here is the analogy I find helpful. Think of a large language model as a giant apartment building with millions of rooms. Each room is a single weight in the model. When you train the model, you are deciding which rooms to renovate and how heavily. Supervised fine-tuning is like doing a full renovation. It opens nearly every room and makes significant changes. Almost 93% of weights get visibly modified. Reinforcement learning is extremely selective. It touches only about 23% of weights, and the ones it touches are deliberately chosen to avoid the most load-bearing structural walls, what the researchers call principal directions. On-policy distillation lands in between, touching about 46% of weights, and like reinforcement learning, it also prefers to work in the lighter load regions rather than the structural core. The researchers call this a relaxed off-principle regime.
Why would a training method prefer to avoid the principal directions? What is actually happening there, and why does it matter?
This gets into something beautiful about how neural networks store knowledge. The principal directions in a weight matrix are essentially the highest leverage dimensions, the directions that most strongly define what the model already knows how to do. When you do supervised fine-tuning, you aggressively modify those high-leverage dimensions because you are rewriting the model's existing knowledge with new demonstrations. When you do reinforcement learning, you are more careful. The model is learning from its own experience and trying not to forget everything it already knew, so it gravitates toward the lower curvature, less critical regions of the parameter space. Think of it like renovating a building. Reinforcement learning prefers to modify the decorative panels rather than the structural beams. On-policy distillation does the same thing, but because the teacher is giving dense guidance at every token, it opens more rooms in those non-structural areas. It is geometry preserving like reinforcement learning, but broader in scope.
Okay, that makes sense as a static picture. But you said the really surprising finding is about the trajectory over time. What actually happens as training progresses?
This is where things get genuinely strange and interesting. If you track the dimensionality of the updates over training, meaning how many distinct directions in weight space are being modified, you see three completely different stories. Supervised fine-tuning keeps expanding its update subspace as training goes on. It keeps recruiting new dimensions of the weight space throughout the whole training process. Reinforcement learning does the opposite. It starts more spread out and contracts toward a narrow low-dimensional channel as training proceeds. On-policy distillation does neither of those. From almost the very beginning of training, it locks into a narrow low-dimensional channel and stays there. It does not expand like supervised fine-tuning, and it does not gradually contract like reinforcement learning. It finds its groove immediately and stays in it.
Hang on, could that just mean that on-policy distillation is not actually making much progress? Maybe the updates are small and trivial, and that is why they stay in a small space.
The researchers anticipated exactly this concern, and they directly tested it. They measured not just the shape of the updates, but also their magnitude. And what they found is that on-policy distillation actually accumulates substantially larger updates than reinforcement learning in terms of raw magnitude, while ending up with a comparable narrow dimensionality. So it is moving a lot through parameter space, but moving along a narrow corridor rather than spreading out in all directions. This is not a small update artifact. It is a genuinely bounded spectral profile of a large and meaningful update. Think of it like water flowing through a canyon. A huge volume of water can move very fast through a very narrow channel.
That is interesting. But here is what I really want to push on. You are measuring the geometry of weight updates. How do we know this narrow channel is actually meaningful for the model's ability to reason and solve problems, and not just an interesting mathematical curiosity?
This is where the research gets really clever. The researchers ran a direct functional test. They said, if this narrow channel that emerges in the first 20% of training is actually the channel that matters, then we should be able to constrain all future training to stay within that channel, and the model should do just as well. So they extracted the 16 most important directions from the early update subspace, and then forced all subsequent gradient updates to live within those 16 directions. For on-policy distillation, performance was essentially unchanged across 5 different reasoning benchmarks. For supervised fine-tuning, the same constraint caused a substantial degradation. This proves the channel is not just descriptively narrow, but functionally sufficient for on-policy distillation.
16 directions out of a weight matrix with potentially millions of parameters. That is an extraordinarily tight constraint. I find it hard to believe that works without losing something.
The numbers are striking, are they not? The researchers themselves note this is a stringent bottleneck, chosen to be slightly below the natural effective dimensionality they observed. And yet the performance holds across AIME 2024, AMC 2023, AIME 2025, Minerva, and beyond AIME benchmarks. The fact that supervised fine-tuning breaks under the same constraint in the same experimental window makes this result more compelling rather than less. It rules out the possibility that 16 directions is just somehow always enough for any training method. It is specifically sufficient for on-policy distillation.
So let me ask the follow-up question. What is actually causing this locking behavior? Is it the fact that you are using a teacher model, the fact that you are generating your own data, the specific tokens you train on? What is the mechanism?
This is the third major finding, and it required a series of careful intervention experiments. The researchers tested three candidates. First, token density. What if you only train on the tokens where the student most strongly disagrees with the teacher, cutting down to 25 or 50% of tokens? The lock held. The update scale changed modestly, but the narrow, low-dimensional profile remained essentially identical. Second, rollout policy. What if instead of generating data with the student, you generate it with the teacher? This is called off-policy distillation. Again, the lock held. The dimensionality trajectory matched the on-policy version closely. Third, the objective itself. What if you mix the on-policy distillation signal with a reinforcement learning reward signal? This changed everything. When the on-policy distillation component became weak, the rank trajectory departed from its locked profile and entered a completely different spectral regime.
So the mechanism is in the objective function itself, not in the data collection process. That is a clean result, but I want to play devil's advocate on the whole study. This was all done on one family of models, the QN3 family, on math domain tasks. How confident should we be that these findings generalize?
This is a legitimate and important limitation that the researchers are explicit about. All experiments use QN3 family models on mathematical reasoning tasks, with some robustness checks across different model sizes and teacher scales. The authors directly state that the geometry they observe may vary across other model families, modalities, and task distributions. The three-gate theoretical account they offer is consistent with the evidence, but it is a mechanistic explanation rather than a formal proof. So the honest interpretation is, these results establish that on-policy distillation has a distinct update geometry in at least this well-controlled setting. The theoretical account is plausible and parsimonious, but broader validation across different model architectures and domains is the natural next step.
What about the three-gate theory you mentioned? Walk me through the logic there, because I think it is the heart of why on-policy distillation lands where it does.
The three-gate theory was originally developed to explain why reinforcement learning ends up with sparse, off-principle updates. The first gate is a distributional anchor. The model cannot move too far from its current position in policy space, or it forgets too much. The second gate is model geometry. Given that the update size is bounded, the landscape of the pre-trained model steers the updates away from the high curvature principal directions, because those are expensive to change without breaking things. The third gate is numerical precision. At 16-bit floating point precision, only updates above a certain size actually register as visible weight changes. The researchers extend this theory to on-policy distillation and argue that all three gates are still present, but the second gate is relaxed. In reinforcement learning, the teacher signal is just one number per sequence. Did you get the answer right or wrong? In on-policy distillation, the teacher signal varies at every single token. This richer signal broadens the set of directions that get updated without removing the geometry-preserving bias. More rooms get renovated, but they are still chosen from the less load-bearing parts of the building.
And the implication is that if you want to improve on-policy distillation, you should be thinking about how to control the geometry of updates rather than tweaking the token selection strategy or the data generation pipeline.
Exactly. And this is one of the most practically actionable parts of the paper, because right now, a lot of work on policy distillation focuses on which tokens to train on, how many samples to generate, what size teacher to use. The research suggests those dials are downstream of the real lever, which is the objective composition. If you want to steer the update geometry, you need to think about what objective is being optimized, not about runtime parameters. And because the update channel locks in so early, the researchers suggest that practitioners should monitor this channel during training and use objective composition as the primary correction tool if the geometry starts drifting in an unhealthy direction.
So the practical takeaway for someone building these systems is pay attention to what you are optimizing for, not just what data you are training on or how many tokens you use. The math of the objective is shaping the geometry in a way that runtime choices cannot override.
That is a great summary of it. And there is a broader principle here too. We often treat the inside of neural network training as a black box and just measure outputs. This research is part of a growing body of work that opens that black box and finds genuine structure inside. Different training paradigms are not just different in their recipes, but in the fundamental geometric paths they carve through parameter space. That structure is not just an interesting scientific fact. It can be used to build better, more stable, and more interpretable training algorithms going forward.
And that is a wrap for today's episode. If you found this conversation valuable, consider subscribing and turning on notifications. We release new research breakdowns regularly, helping you stay on top of the latest discoveries without having to read every paper yourself. Thanks for listening, and we will see you in the next one. Goodbye.